Okay, so in this piece, we're going to learn how to find area for polar curves and arc length for polar curves. Again, we have basically two formulas here that we're going to want to write down, try to remember. Sorry, that whole thing's not the formula. This formula is equivalent to this formula, right? So to find the area of a polar curve, we're just basically taking 1/2 of the integral of the radius squared from alpha to beta, where alpha and beta are like our theta angles. The reason this piece has an f of theta is just like like if we were given the relation y equals x, sometimes you write like f of x, right? So like here, sometimes you're given the relationship r equals some function of theta, right? We could easily just call this f of theta equals that, right? So it's just like function notation for polar equations. All right, so let's see an application of this real quick. We're trying to find the area enclosed by r equals 2 plus 2 cosine theta on the interval from theta equals 0 to theta equals pi. So basically what we're going to need is we're going to need r squared. So let's go and find r squared first, right? R squared is going to equal 2 plus 2 cosine theta, and we're gotta square it, right? When we square it, we're basically just foiling it, right? It's going to be 4 plus 8 cosine theta plus 4 cosine squared theta, right? If you're confused about where I'm getting this, just write out this and do FOIL, right? And you'll get this, right? So that's r squared. So now we can say, okay, well, the area is going to equal 1/2 of the integral from 0 to pi, right? Those are the limits they gave us, of the radius squared. So of this thing, we already found the radius squared is this. Right, with respect to theta. And then, if you have a calculator, you integrate it on the calculator while you're in polar mode, right? Make sure you're in polar mode for that. If you don't have a calculator, then you have to try to do this by hand. What I'd like to do is look at like a Desmos graph real quick. Okay, so this is what the graph looks like on Desmos. And the idea is we're going to basically find the area of this region here, right? We're going to find the area of this thing. Okay, so in order to integrate this, we need to use some trig identities and clean it up a bit. So the first thing we're going to do is we're going to factor out a 4, right? When we factor out a 4, it's going to be multiplied over here by this 1/2. So it's going to give us a factor of 2, right? 4 times that is going to give us 2. What's going to be left is 1 plus 2 cosine theta plus cosine squared theta d theta. Integrating these two is no problem. Integrating this is not just sine squared theta, right? Hopefully you don't think that it is. In order to do this one, we need to use the trig identity that cosine squared is the same as 1/2 of 1 plus cosine 2 theta. All right, so we're going to go ahead and replace this cosine theta with 1/2 of 1 plus cosine 2 theta, which I guess maybe a better way of writing that, an easier way of writing it would be just like distributing the 1/2 in there again, right? So like actually writing 1/2 here and 1/2 there. Maybe that's going to be easier to integrate. We can go ahead and integrate now. It's going to be 2. The integral of 1 with respect to theta is theta plus 2 sine theta plus, this is going to be 1/2 theta plus the integral of cosine 2 theta is sine 2 theta over 2, so there's an extra 2 right here. And then we have to plug in 0 to pi. So what this is going to give us is, let's see here. Maybe it'd be easier just to distribute this in there first, just to cancel out some of the weird things going on. This would be 2 theta plus 4 sine theta plus theta plus sine 2 theta over 2, right? That 2 is going to cancel with one of those 2's. We still got to plug in 0 to pi. We can clean it up a little bit here. This and this will add together to give us 3 theta plus 4 sine theta plus sine 2 theta over 2 from 0 to pi. So we're going to go ahead and plug in pi. We're going to get 3 pi plus 4. Sine of pi is 0, and sine of 2 pi is also 0. So this is going to give us 3 pi, right, as our answer. We can check real quick by plugging into our calculator. Let's get that up here real quick. I think I tried this already somewhere. If we integrate that function, we get, right, so I have it here. If we integrate it, we get 9.4, which is the same as 3 pi, right? So 3 pi is our answer there. Again, trig identity needed. What I recommend is go to Purple Math and look at all the trig identities. There's a bunch on there that will be useful. Okay, let's look at arc length for polar curves. So here with arc length, again, we're integrating the square root of r squared plus dr d theta squared. In this case, with the example we're going to be trying to do, we're given r equals e to the theta. We're going from 0 to pi. So let's go ahead and set it up. The arc length is going to equal the integral from 0 to pi of the square root of r squared. R is e to the theta, so we're going to do e to the theta squared, plus we need dr d theta to put it in there. So let's do dr d theta over here. If we take the derivative of r, we're going to get e to the theta, right? It's itself. So that's nice. So we can just put e to the theta there. And now again, the trick becomes like, if we had to do this by hand, how would we do this? So let's use some properties of exponents. This is going to become e to the 2 theta, right? A power to a power, you multiply the powers. Plus, this is also e to the 2 theta. So this is going to equal, I have the same thing added to itself. So that's e to the 2 theta plus e to the 2 thetas. There are 2 e to the 2 thetas there. If we can remember that square roots are the same as raising something to a 1/2 power, then we can say, oh, well, this is the same as 2e to the 2 theta raised to the 1/2 power. Then this 1/2 can distribute into the exponents. So we have, maybe this should just stay as root 2. But this one, when I do 1/2 times 2, I get e to the theta. And then we can integrate this, which is going to be, since it's e, the integral is itself from 0 to pi. So we're going to have root 2 e to the pi minus root 2 e to the 0. E to the 0 is 1, so we're getting root 2 e to the pi minus 1 in that case. And, sorry, not minus 1, minus root 2, right? Because e to the 0 is 1, and we have the root 2 there. Okay, so that's that one, right? And again, that's not going to be all the cases, but there'll be other cases you could look at. Okay, I guess this one wasn't that long, so I can do vector valued functions. Let me just get this set up for vector valued one. Okay, integration of vector valued functions. If I integrate a vector, remember a vector is like the x piece comma the y piece in these like triangular brackets. Basically, I can just integrate the x piece and I can integrate the y piece separately. If I want to know the length of a vector curve from A to B, then basically I have to integrate remember this means magnitude of the derivative of the vector valued function. Okay, so let's do some examples like this, right? We are given the acceleration vector is e of t, and the x piece is e to the t, the y piece is e to the 2t. At time t equals 0, its velocity is I plus j, which all this means is 1, 1, right? This is 1i, 1j. This is like the x piece, the y piece. Its displacement is 0. Find the functions for the position at the velocity at any time t, right? So what we have to do here is, since we're trying to find velocity, we need to integrate the acceleration, right? So the velocity is going to be the integral of the x piece and the y piece, which turns out just to be e to the t and e to the 2t over 2, right? Just integrated the x piece and the y piece. And then we have to remember that there would be like a plus c in there somewhere. Because that plus c is going to come on this piece here. And the idea is we know that at time t equals 0, we should be getting this vector, 1, 1. So, which means if I plug in 0, I need this vector to turn into 1, 1. So, the x piece is fine. The y piece, we need to figure out what c is, right? So basically this is 1/2 plus c needs to equal 1, right? Like this needs to equal this. So what is c is? C is 1/2, right? So that tells us that c is 1/2, and so our velocity vector is e to the t, comma, e to the 2t over 2 plus 1/2. Right, that's our velocity vector. Now we want to find our position vector. We can just integrate again. So our position vector is just going to be, well, this one's still e to the t. This one's going to be e to the 2t over 4 plus 1/2 t plus c, like that. And in order to figure out what the c value is here, it tells us that the displacement was 0. So we need to use that fact to find what the c value is. Displacement being 0 means that the function, basically you're getting this vector out of it, right? You're getting a vector that has no length to it whatsoever. So what that means, if I plug in 0, I should get a vector that is, I should get a c value that makes this 0, right? So we're going to set e to the 0 over 4 plus 1/2 times 0 plus c has to equal 0. So this is 1/4 plus c equals 0. And so we get c equals, c would be negative 1/4. There's something wrong with this, because, oh, you know what? We didn't take into account this guy when we did it. Okay, I didn't really want to do this, but I think we have to do this. The other way to write vectors is with like the I and the J thing, right? So like it's a little bit confusing and we haven't talked about that much, but writing this vector is the same as writing e to the ti plus e to the 2t over 4 plus 1/2 t plus c j. And and sometimes it's just a way of writing it out so you can like do like have it look like an equation. And when we do this, we should get 0. So please ignore this. This was wrong because this piece can't be 0. This piece has to be, this has to be something else. But when we do this, the displacement should be 0. So we should be getting 0 out of this when we plug in 0. So basically what we have is I plus 1/4 plus Cj equals 0. We're trying to figure out what C is. So we're gonna basically solve for C, which means we could distribute. Let's start by distributing the J. We're gonna have 1/4 J plus Cj. Right, and then we can no, the C is not, oh man, the C is not part of the J. The J is only on this, and the C gets added over here. So, my apologies. This is the J piece, and the C is over here by itself with no J on it. So when we do this, we don't have to distribute it in. We can simply subtract I on both sides and subtract 1/4 J on both sides. And so we're going to get C equals 1/4 negative 1/4 J minus I, which we usually write the I first, so it's going to be negative I minus 1/4 J. That's what C is. So if we rewrite our entire function, it's going to be e to the t I plus e to the 2t over 4 plus 1/2 t j, and then plus c, where c is negative I minus 1/4 j. And then we'd put all the I pieces together, so it'd be e to the t I minus I plus e to the 2t over 4 plus 1/2 t j minus 1/4 j. And then you can, for each piece you can like factor out like the I piece, so you'd get like e to the t minus 1 I plus, and then in this case you get e to the 2t over 4 plus 1/2 t minus 1/4 j. And so your vector is basically just the x piece is the piece next to the I, and the y piece is the piece next to the j. So it should just be e to the t minus 1 comma e to the 2t over 4 plus 1/2 t minus 1/4. And so this is our position vector. So I feel like I probably didn't do a great job of explaining that, so maybe at some point we can do different examples with that. Let's look at the length of a curve for a vector real quick, because I think this is actually easier than what we just did. The length of the curve, again, is going to be the magnitude of the derivative. So we need to find the derivative of this, which r prime of t is just going to be the derivative of each piece. So it's 2 cosine t, negative 2 cosine t, and then 5. The magnitude, remember, is basically the distance, which is the x piece squared plus the y piece squared. So the magnitude of r prime of t is going to be the square root of negative 2 cosine t squared plus 5 squared. And then we have to integrate that, right? So the integral from 0 to pi of this thing. And if we square it, we're actually going to get 4 cosine squared t plus 25. And we can put this on a graphing calculator to help us solve this, because otherwise it's a bit tricky. You'd have to use that trig identity here again. So let's put it on a graphing calculator. We're going from 0 to pi. We're taking the square root for I should we've got to change our mode, yeah. Vectors like parametric, yeah, so let's put it in parametric. 0 to 4, square root of 4, cosine t, cosine t squared. Nope, it's not doing what I want it to do. Cosine t there we go, plus 25. And we're going to get 16.319. All right, so that one's not that bad. Good luck with this. Please ask for help because, it's hard.